Okay. So I don't know why I made that noise, but it is what it is. Okay, so in statistics, there's a definition we should know about statistics. It's not really a big deal. And let me make sure I'm sharing the right thing. Yeah, it looks like I'm sharing it. So in this class, I mean, the definition of statistics is kind of like the science, girls, or art of, what's the first thing you do with data? You collect. Then what do you do after you collect? Organize. What's the next? Yep. And what's the last thing? Yep.
No way.
I'm not sure if interpret spelled that way. The science or art of collecting, organizing, analyzing, and interpreting what? Data. Now, data itself is like information you collect. Usually numerical, but not always. So it's not always numerical. Okay. So data is just, it's counts, measurements, or observations that we're interested. Okay, good. So that's pretty easy. Now, data is divided into two types. There is qualitative, and there's quantitative. Okay. Now, qualitative is categories. It's names. Example. I might ask, how many people have blue eyes in the class? Raise your hand if you have blue eyes. There we go. Of course she has blue eyes. They're the most beautiful eyes in class. That's an opinion though. It's true, right? Yeah. Well, some of you are saying that's not true. Brown eyes are better. No, they're not. I know, guys. It's an opinion. It's an opinion. I know it's an opinion, but like I look at a girl with blue eyes, and it's like, oh my gosh, I fall in love. Right. How many here have the basic brown eyes? I'm sorry. Don't feel bad about it. All right. So an example is blue eyes. In this class, we have one. Who has green? Okay, so we have people with green eyes. I hate you too. We have two with green. So this is categorical. We can't really do math with it. And then brown eyes. Everyone else. Everyone else. Okay, by the way, brown eyes is like the eye color of humans. In the end of the day, if you have blue eyes and you marry somebody with brown eyes, is the most common color in the world. All you gotta do is if you go to India, if you go to China, it's brown. Okay? If you go to Africa, it's brown. They're all blue eyes over there. Like it's incredible, man. It's incredible. But if they mix with somebody with brown eyes, the lineage starts getting diluted in brown eyes, and it'll go away eventually, which is what's maybe gonna happen. And now my sister's bothering me. Sends me a document. Okay. All right. So that's what it means, guys. Like I might also ask, like, how many people are wearing white shoes in the room? And we just, white shoes, if they get dirty very easily, don't wear them, right? So, okay, now, so that's categorical data. With categorical data, you can't really do a lot of math with it. Not as much as you would want to do. There's very little math you can do with categorical data. But with quantitative data, this is numerical. These numbers might make sense. It might be the heights, it might be weights. Okay. It could be money. All right. You can do a lot of math with quantitative, and quantitative is divided in two sets. Discrete and continuous. So there we have two types of data. And then within quantitative, we have two types of quantitative data. So discrete data, the main thing you got to get from discrete is that it can only be countable. It can be 1, 2, 3, so on. This means it's countable. Ladies, please pay attention. It's countable. That's the key word with discrete. With continuous, it means that it's measurable. That's a key word, measurable. Like you can have 1, but you can also have 1.1, or you can have 1.21, you can have 32.0, 32.1. It's, see, while discrete, you're just counting. In continuous, you can have 1, but you can also have the numbers in between 1 and 2 and all those other numbers. But discrete doesn't allow that. Discrete is just counting. When you count, I don't care if like one of you here is missing like half your body. You're not half a person. You're still a person. You still have we still count you as a full person. Not as more specific. It's look, all right. Are people 1 foot tall, 2 foot tall, 3 foot tall, 4 foot tall, 5 foot tall, 6 foot tall, or can they be in between 5 and 6? And it's along a continuum, continuous continuum, like that. But discrete is da, 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 da. It's coming out here in the video too. Da, da, 3, 4, and there's nothing in between. Got it? Okay. The fist means 1, 2, 3, 4. Now, all right. We're not going to get into the philosophy of this because when we collect data, it comes in discrete points. But the nature of the data could be continuous or could be discrete. That's what's important. All right. So they gave some definitions there. You can look it up. You're gonna have to have this book on the PDF because there's not enough for everybody. So we'll take a roll. See, I guess give the book to serious students. Okay. So now we can talk about stem and leaf diagrams. So now we're going to go straight into stem and leaf diagrams. Stem and leaf. So let me scroll the board up. All right, so stem and leaf. Let's talk about this. So here's what we got. We have, I say a group of data. I started measuring like, I don't know, the weights of the people in this class. And the first student weighs 132 pounds. The next girl weighs 172. The next girl after her weighs 201. But then this other girl weighs 120, but this guy here weighs 150, but this other guy weighs 115. Oh, poor guy. Let's just make him a little bit heavier because I'm just 121, so he's not the lightest person in class. And then there's this person at 183 and this person at 163, so on and so forth. They get somebody in the 130, 133, 134, 137, 157, 172, 128, 127, 122, 148, 147, 121, 155, 155, 200 again. So these numbers are there. These are all the numbers. Great, fine and dandy, awesome. All right. They're out of order, which is fine. It can also be out of order, but let's do something called stem and leaf. Now, here is a stem, and here is a leaf. And I ask you, what's the smallest stem here? It looks like 1, 2 would be the smallest stem. So since this is 3 digits, we're going to use the first 2 digits for the stem. But if we're 4 digit, we might use the first 3 digits for the stem. So this is 1, 2. Then you got 13, 14, 15, 16, 17, 18, 19, 20. The biggest stem is 20 for 200. And then you make a line like this. And then you read 132 and you say, here's 132. And then you do 172, and here it is. And then you have 201, here it is. And you have 120, here it is. And you have 150, here it is. And you have 121, here it is. And you have Okay. Well, what number am I right now? I'm 183, right? I'm here. 183. Look at the next one, 163. Look at the next one, 133. Look. Then the next one's 134. 137. 157. 172. 128. 120. Let me make that 8 prettier. 120. 140. 140. 120. 150. 150. 200. This is called a stem and leaf plot or diagram. When I'm done with the stem and leaf, I should let my audience know what the key is. And I give an example here on how to read it. I might write 113/3 signifies 133. This, it's a lot of noise, but it's just make believe. All right, 13.
I think sometimes you're
13/3 means 133. You're telling your audience how to read your stem and leaf plot. Now, another interesting thing about a stem and leaf plot is it conserves all your numbers. It preserves the individuality of the data points. If you turn your head to the side, you would also see that you have like a little histogram going on here, a bar graph that shows you the shape of the data, some shape. But you got to turn your head to the side. Now, this here is referred to as an unordered stem and leaf. Now we're going to make this into an ordered stem and leaf. And when we do that, we end up having all the numbers in order. So we assume we collected the data, and this is a way of organizing the data, part of our definition. So we say 0, 1, 1, 2, 7, 8. I just put the 120s in order. And now I'm going to put the next one in order, which happens to be already in order. But the next one now is in order. And the next one now is in order. and the next one was in order, and this one didn't, whatever, and this one, whatever. This one stays blank and 0, 1. And now this, I'm gonna put my key here. I'm gonna pick a different key just to make a point. Notice that this number, the key I picked, the number doesn't exist. That's not the point. The point is so the audience knows how to read it. Because this could mean 12.9 for all I care. And that would have been your stem, your stem and leaf. That would have been your key, how you read it. In this case, 12.9 means 129. And this here is called an ordered stem and leaf. Any questions or concerns? Yes. Your stem is smaller. So let's say you picked 53. There's 53. Your stem for 53 is 5. So your leaf is 3. Okay, so he said when it was 2 number, when it was 4, it would be 3. Yeah, usually. Now, sometimes you have to make it creative, but we'll talk about creativity later. For now, you know, the first quiz that you're going to take is going to ask you these definitions. It's going to ask you how to do a stem and leaf, you know, which I think everybody here should be able to do a stem and leaf. Okay? There's nothing hard about it. Well, another little detail about this, how many numbers do I have for 120? It'd be 1, 2, 3, 4, 5, 6. They like putting a parentheses with a 6 here for counting purposes. Parentheses and 4, parentheses and 2. This is for a count. They love doing this. I don't know why, because it could be confusing. Okay. They like doing that, but that's to give a count. 6 plus 4 is 10, plus 2 is 12, plus 4 more is 16, plus 1 is 17, plus 2 is 19, plus 1 is 21, plus 2 is 23. There's 23 numbers. Are there 23 numbers? I think there might be. Guys, I think I'm missing a number. So let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. 1, 2, 3, 6 plus 4 is 10, 16, 17, 18, 19, 20. Oh, I got 22. There's 22 numbers. I'm good. Okay. The next thing I want to teach you or talk about is called a histogram. I'll wait. So this is easy. Everybody should get an A on this. You know, you shouldn't get that question wrong. As far as definitions concerned, I wrote the definitions in there. If you write them, if you're able to explain to me, I'm happy with it. So everybody should be getting an A. Like if you're not getting an A on the next quiz, I'm like, oh my God. It's not, it's just fun. I don't want to kick you out of class, but it's like, really? It wasn't the algebra, you know? Now there's no algebra. What's the problem now? So I'll wait. So I already went to the gym this morning. I've been awake since 3 in the morning. So it's kind of funny. I'm only sleeping 4 hours. So it's possible, and I'm not sleepy at all. I don't know what it is. I don't know what it is. Okay, let's talk about histogram. The next is a type of table we're going to want to do. It's called a histogram. Now, the problem with a histogram is we have a concept with histograms. Okay, so what is a histogram? A histogram is a type of bar graph. A histogram is a type of bar graph where the bars touch, basically. It's only used for qualitative data. Sorry, quantitative, my bad. Quantitative. Okay. So remember, bars need to touch. Now, unfortunately, this book says that the area of each bar is proportional to the frequency. And this is not a problem, but maybe it's something new for some of you. See, in honor stats, all our classes had the same width. So we didn't have to worry about if we had different classes of different widths. Okay? But in this class, we have to start worrying about those little details. But let me introduce it little by little. Okay? Let's do that first. So I'm gonna go ahead and go straight to a problem in the book. So let me make sure it's a nice one. There's no nice ones. There's no nice ones. What can I say? So let's see. There's not a nice one. There's a nice one. There's one nice one. So let's start with that one. So right here, I'm gonna give you something called a frequency. I'll do it in red. A frequency distribution. And I want to create a histogram out of it. So in this case, this measures the height. This measures the frequency. These are in centimeters. And it has 0 to 5. Less than, greater than, equal to. And this is H. It has H is less than 10, but bigger than or equal to 5. Then it has 8. Be careful. 15 greater than equal to 10. Less than 20, greater than equal to 15. Less than or equal to 20. Less than 25, greater than equal to 20. And less than 30, greater than or equal to 25. And we have 3, 5, 11, 6, 3, and 2. This is a frequency distribution. And we're going to create a frequency histogram. So we begin. We make an axis. Smallest number is 0. Then it goes to 5. Then it goes to 10. Then it goes to 15. Then it goes to 20. Then it goes to 25. Then it goes to 30. And these are heights. So I'll label this heights. And then here is frequency. Frequency is always on the vertical axis. And I'm going to go ahead and do, I don't know. I'll do it by twos. 2, 4, 6. Pick a scale and keep to it. Whatever scale you pick must be consistent. Okay. So from 0 to 5, there's 3. So I can go ahead and do 3. Some of you might want to put a 3 here. And then 5. And then 11. That's really bad. It shouldn't be skinnier, but that they should be the same width. In this case, because all my class, these here are called classes. Okay, they're like intervals. Okay. All right. So this is, you could call this a grouped frequency distribution. Technically, these are classes. All right. Since they're all the same width, all my bars should be the same width. So I'm being sloppy, but you get it. From 15 to 20, that's 6. See, they're also, it looks weird. This is a big deal. It actually is a big deal that those bars be the same. And then you have 3 here. So 3, you have 6 here, and then you have 2. And so that's a histogram right there. Now that is simple enough. And it's and on our stats, that's what we did. All the bars were the same width. But in this class, we don't end there. So I want to go ahead and under that one, do another one. But we're gonna start talking about what it means that the area of the bar is proportional to the frequency. And in that case, we're gonna have a class that either is wider or smaller than the other ones, or we're gonna have an open class that goes on forever. And we have to have rules on how to deal with it. And there's where studying this and doing the homework and asking questions will make a difference on your quiz, because obviously I'm gonna give you the ones that are not easy. I might give you one that's easy, but who cares? A third grader can do it. Can you do the harder ones? I'll do it on the phone. There you go. All right, there we go. Sat down. Okay, so right now, we're going to talk about, I'll do this in, oh man, I zoomed out. I'm going to go ahead and create here the same type, you have height here. You have frequency here. I'll just put F for frequency. You have 0 less than 5, greater equal to 0. You have 5, and then you have H, and you have 10. So less than, greater equal to. Then you have H less than 15. So far, so good, actually. Then you have this guy here. So far, no change, but look what I'm gonna do in the last one. What happened there in the last one? And with the width of the class. Isn't the last one wider? Yep, and that's problematic. Because if I were to graph this, you would have 0, 5, 10, 15, 20, 25, 30, and you would put frequency here, 2, 4, 6, 8, 10, 12. And from 0 to 5, it's 3. And 10 to 5 to 10 is 5. And then 10 to 15, it's 11. And the 15 to 20 is 6. But now from 20 to 30, it's 5. And it's going to look like this. And that's a problem. Because now that bar there, see, let's do something here. Let's add up all these frequencies. 5 plus 3 is 8, plus 11 is 18. 19, sorry. 19 plus 6 is 25. Plus 5 more is 30, so there's 30 numbers. Now, I'm going to do something called relative frequency. What's 3 divided by 30? 3 divided by 30 is 0.10. It's 29. Oh, man, that's a horrible number. 6 plus 5 is 11, plus 11 is 22. 22 plus 8. Okay, damn, it's going to be horrible numbers. So 3 divided by 29 is? Oh man, give me 1 second. My wife is saying if the doctor called me, and the answer is no. All right, so the first one will be 0.10 anyways, it's close enough. I'll put 0.1, 0.10. Yeah, to make it prettier. Yeah, let's just keep it like the book wants it. It doesn't matter. So this is 3 divided by 29. That's 0.103. Then the next one will be 5 divided by 29. That's 0.172. And then you have 11 divided by 29. That's 0.379. And then you have 6 divided by 29. That's 0.207. And then we have 5 divided by 29. And what is it? 0.172. Now, each of those relative frequency represent how much of that data takes up from the total. So the biggest one there is from 10 to 15 is taking up more than a third of the data. Now, let's do the area here. What's 5 times 3? What's 5 times 3? What's 5 times 5? What's 10 times 5 times 11? What's 5 times 6? What's 10 times 5? Do you see the problem? That guy cannot be as big an area as 55. It must be proportional. Okay? It has to be proportional to its relative frequency. So in order for the graph, the histogram not to be misleading, we need to allot. We need to make an adjustment. And we call that a frequency density. Okay? So what it's supposed to be is you're supposed to say, well, the width of the class times the height must equal the frequency. So the height must equal, oh my gosh, give me 1 second. The height must therefore equal the frequency divided by the width. And this is called a frequency density. It's called a frequency density. So if we were to do this graph correctly, first of all, we don't use frequency. I'm gonna paste it down here. We will create, let me lasso it again. We would actually create here a separate category. The moment we have, I'll put FD. The moment we have one of our classes that is not the same width as the other, we need to, instead of Using the vertical axis frequency, we had to make something called frequency density. So what do? We take 3 and divide it by the class width. Okay, what is 3 divided by the class width? Okay. I should tell you what the class width is. The class width is done this way. What's 5 minus 0? 5. So you should take 3 and divide it by 5. 0.6. And I don't have space there. So let me make space because this is going to get kind of crowded very quickly. And then the next class here is 10 minus 5, which is 5. So 5 divided by 5, which is? And the next one is 10 minus 5. That's 5. 11 divided by? Which is what? 2 point what? 2.2. So that's 2 1/5. The next one's also a class width of 5. 15 minus 10 is 5. So that's 6 divided by 5, which is 1.2. And the last one, the class width is 10. What's 5 divided by 10? What's 5 divided by 10? Now, if you add up all your frequencies now, what do you get if you add up all your frequency density, sorry? If you take 0.6 plus 1, it's 5.5. And can you take 0.5 and divide it by 5.5 and tell me what you get? So, okay, 0.5. Give me 1 second, I'm adjusting this. Wait, I added a total here and it's different, guys. Let's try it again just to make sure. But I'm using this calculator here that doesn't let me. .5 is correct. .09. So now here's what we do. Over here, we do frequency density. And all this goes. We don't use this anymore. And now we pick a scale. I'm going to go ahead and pick the scale of 0.5, 1.0, 1.5. This is not a good scale. I'm just going to go 1, 1.0, 2.0, 3.0. I'll eyeball everything, but you shouldn't do this on the test. The other scale, 0.5, was better. So for this one, you'll put it at here. For this other one, you would put that should probably be a little bit smaller. The next one you put at 2.2. Se me pasé. 2.2. The next one will be 1.2. And the last one is 0.5. And the last one is 0.5. So, yeah. But in reality, what I'm trying to explain to you is we made the adjustment. We made the adjustment for the bar. Because this guy here is proportionally too big in comparison to this one. The relative frequencies to show you that this here only represents 17% of the data. Does this look like 17% of the area, or does it look like it's going to be more? Well, let's see. What's 55? Let's do it in order. 15 plus 25 plus 55 plus 30 plus 50. 5, 10, 15. Carry the 1. 5 plus 3 is 8. Plus 5 is 13. 2 more is 15. 16, 17. Take 50 and divide it by 175. And now you realize that that bar, this calculator here is, every time I touch it, I press 3 numbers at the same time. You get 28.5% of that, 28.6% of the data. So this is 28.6% of the data. No good. So let's do it here. What's 5 times 0.6? 5 times 0.6, we got 3. So this is going to be 3. 5 times 1 is 5. 5 times 2.2 is what? 11. What's 5 times 1.2? 6. And what do you think 10 times 0.5 is? Did you notice that these numbers came out to be the frequency of these? And now what happens when you take 3 plus 5 plus 11 plus 6 plus 5? You get how much is the total? As you guys corrected me, 29. And what's 5 divided by 29? And that's why I did the relative frequencies, so you can see that. And nobody's seeing anything that I'm doing because nobody wants to get up and do this. Do you see how when we did the area here, it came out to be the frequency? See it? And then when I take 5 and divide it by 29, guess what? Is this proportional to the relative frequency? Yeah. Yes. And we adjusted the height of our bar for the area. Do you see that? And that's called a frequency density. And we have to use it when we have that situation arising because we don't have equal widths in our classes. So that's one situation. Yes. Okay, so relative frequency, I determine it like, I'll just write you an example right here. And it's 3 divided by 29. It's 5 divided by 29. It's the whatever the frequency is for that particular class divided by the total. It's another way of rewriting the frequency so that you can compare it to the whole. It's a decimal or percent if you want to convert it. Because when I look at 11, I see 11, but when I see 0.379, I see that's a substantial portion of the data, about 37%, 38%. Make sense? Okay, but of course they can't just leave it like that. Okay. They have some rules. Okay. That are important. And do you guys copy that or should I wait? Yes or no, or maybe, or sort of, kind of? Yes, maybe, sort of, kind of. No? No. Yes. Yes. Okay. So, do we have time? We have plenty of time. So, but sometimes they have, I don't drag that up. We can have a possibility of having an open-ended class. Oh. What do I mean by that? What do I mean by an open-ended class? That means it doesn't have a second number in it. So let's say this is a good example in the book. And I'm making sure I'm trying to shadow the book. So in this case, these are weights or masses, which is different than weight. Here's mass. Let's say it's 101 to 110. This is 1. 111 to 120. This is 4. 121 to 130. This is 2. 131 to 140. This is 7. 141 to 150. This is 2. And then over 150. This is 4. This is open-ended. We don't know the class width of that one. So here's what we do. I mean, what is the class width here for the first one? Like, what is the class width here? I'll write class width here. I'll make a little line here. Tell me what's a class width for that first class? It's not 9. It's 10. Because the way we do it is you take this one and subtract them. That's how we do our class width. So our class width is 10. What's the class width for this one? What's 121 minus 111? 10. Good. So this so far so good. Same width. What's 131 minus 121? What's 141 minus 131? Okay, so the last one would be, well, over 150 means 150 and beyond. What's the this one should be sorry. This one should be 151 and beyond to be consistent. So what's the class width of 141 to 150? It'd be 10, right? So now let me ask you a question. What is the class width of the last one? That's the rule. You make it twice the previous one. That's it. You got to remember that. And guess what? You can't use frequency here. You have to use what? Frequency density, which you're going to take what? Your frequency and divide by your class width. Got it? So 1 divided by 10, 0.10. 4 divided by 10, 0.40. 2 divided by 10, 0.20. 7 divided by 10, 0.70. 2 divided by 10, 0.20. 4 divided by 20, what? 2. 4 divided by 20, 0.2. 0.20. And you graph this. Now, something I should talk about. Remember, somebody must have gathered this data. Like, something I should mention right now, and this is super important. You cannot recreate the original data from this grouped frequency distribution. In exchange for having the simplicity of this frequency distribution, you've lost information. You no longer can recreate the original data points. That's the exchange. Every time we organize the numbers further and further, we could run the risk of losing the individuality of the data. But in exchange, we can better analyze the data because there might be thousands and thousands of data entries. In this case, you can imagine somebody measuring whatever it was they were measuring, all right, of pebbles in this case, and recording the masses. And then they created the classes, and they then said, okay, this is how many pebbles we had from 101 to 110 grams. All right, we had one of them. From 111, we had 100, and through 120, we had 4 of them, and so on. Any questions or concerns so far with respect to a frequency histogram? Be careful. Okay. Now, there's one last graph we'll be discussing, and we'll be done with chapter 1. And after review next class, you'll get a quiz. So next class, we'll review at the beginning of class. We'll go into trig, and you'll prepare for your quiz for chapter 1. If I have time, I'll also do chapter 2 very quickly because it's very easy. It's just mean, median, and mode. All right. So this class that I'm doing with you guys is a class I take 3 weeks in stat and honor stats to do. There's nothing else to it. I mean, it's just that it's easy. Okay. It's common sense. Now, the next graph we're going to talk about is called a cumulative frequency graph. Okay. Sometimes this is referred to as an ogive. Ladies, I'm going to have to separate you guys forever and ever and ever. So what is a cumulative frequency graph? Well, a cumulative frequency graph is a running total of your frequency. And it's helpful. And it's helpful sometimes. It's another way of looking at data. Again, what are we doing here? We're organizing the data that's been collected into a graph, into a visual representation. So you might have, I don't know, if you look up top here for the mass, let's say I rewrite those numbers, doesn't matter. It's 101 to 110, 111 to 120, 121 to 130, 131 to 140, 141 to 150. Okay, and 151 and beyond. You know what? I'm gonna do 151 just to make it easy. I'm just gonna say it's to 160. I'm gonna write the frequencies down: 1, 4, 2, 7, 2, 4. You know, if you add all these up, you get some number there. So 4 plus 1 is 5, plus 2 is 7, plus 7 more is 14, plus 2 is 16, plus 4 is 20. So there we have our group frequency distribution. Okay. So how do we do this? Well, the first thing we have to do is what we call this relative frequency. Sorry, cumulative frequency. Cumulative frequency. I'll just use CF. CF. This stands for cumulative frequency. And I ask you, by the time I get to 110, how many numbers would I have counted? How many pebbles would I have counted? Sorry. 1. From 101 to 110, I would have counted 1 pebble. But the time I get to 120, how many pebbles would I have counted? Yes. And by the time I get to 130, how many pebbles would I have counted? And by the time I get to 140, how many pebbles would I have counted? And by the time I get to 150, how many pebbles I counted? And by the time I get to 160, how many pebbles would I have counted? Which makes sense. That's a running total. That's cumulative, accumulates or something like that. And notice that this number here is the same as the sum of the frequencies. Does this make sense? Now, in order to graph this, we have to create something called a class boundary. We have to create something called a class boundary. We can't use these numbers straight up. And these are our classes right here, by the way. This is our class, cis. It happens to be mass. So what is our first class boundary? The question I'll ask you is, what is the gap between 110 and 111? How much is the gap there? 1. And my goal is to close the gap between them. That's my goal. So what number would I pick that's perfectly in the middle between 110 and 111? It'd be 110 point. How about for the next one? Wouldn't it be 120.5? And wouldn't the next one be 130.5? And wouldn't the next one be 140.5? And next one 150.5? And next one would have to be 160.5 to be consistent. Well, if I were to repeat this on the left side, this one would be 100.5. This one would be 110.5. This one would be 120.5. This one would be 130.5. This one would be 150.5. And this one would be 100, sorry, this is 140.5. This is 150.5. Notice that there's no gaps between the classes now. These are called our upper class boundaries, and these are our lower class boundaries. So how do we graph this? Well, here we go. This is cumulative frequency. 2, 4, 6. I pick a scale, must be consistent. These are masses. I label my x-axis. This here is my first lower class boundary, and then everything else is just the upper class boundaries. I ask you the first question. How many numbers are 100.5? Are there any numbers of mass 100.5? There are not. But by the time we get to 110.5, how many numbers would I have counted? By the time I get to 120.5, how many numbers would I have counted? And by the time 130.5, notice this is not a bar plot graph. This is it's going to end up being a line graph. By 140.5, it'd be 14. By the time I get to 150.5, oops, I should have done a better job of that. Let me make it prettier. I get 16. And by the time I get to the last one, I have how much? Boom, 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 boom. That's how you create a cumulative frequency graph. What did you add to 110 to go 110.5? What would you add to 110 to get 110.5? You would add 0.5, right? So you add 0.5 to the upper class, you have to subtract 0.5 to the lower class. Because if not, you're gonna change the width of the class. So you have to then consistently do it to everybody else. And by the way, you can see a pattern here. This guy's the same as this guy, and 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 this guy's the same as this guy. And you know the width was 10, 110.5 minus 10 should be 100.5. Depends how you want to do it. Pick your poison. Got it? I hope it's clear. Good. Now, why is this helpful? Well, from this cumulative frequency, you can do a few things, which I'm gonna let the homework do for you. In other words, you're gonna be like, Mr. But you didn't explain this in class. I'm like, I want you to figure things out and be clever. I'll still do it in class. Let me just quickly let me. All right. If you did this, you can represent each of these as percentiles as well. For instance, what's half of 20? 10, right? And so if I take here, I draw a line from 10, and I drag it this way, I hit this. And if I do this, I can figure out the 50th percentile, what it would be. But we'll leave that for later because it's going to come up. All right, I think that's enough for today. Fair enough? All right. It's quite a bit, right? Let's see where it's going to store this because this is going to